As we said, we're trying to get, since we have gotten the reactions, we now want to get the bending moment at various locations. We want to get bending moment at point, we've got a bending moment at point A. Now we want to get bending moment at point C. We'll get bending moment at point C. Put the bending moment at C. Looking at, you must start, we started from point A. Put bending moment, looking at where we started, that's at point A. We call it positive. We have MC, which is positive. Any other moment before it, which is in the same direction with it, is positive. The one against it is negative. So MC, positive. The next load, the first load there is reaction A. So, and the reaction A is against it. So minus reaction A. Reaction A, that is times reaction A times 4. And we got reaction A equal to reaction A equal to 2.11. That means 4 times 2.11. There's no other load before C. At C, we not give moment at C because of no distance. So this is equal to 0. Then that means MC is equal to 4 times 2.11, which is equal to 8 point, which is equal to is equal to 8.44. 8.44. 8 is equal to 8.44 kilonewton meter. That is the moment at C. Next is moment at D. To get moment at D, let the moment look at where we started. We started from point A. So he's looking at, I call it positive. So I have MD. Looking at where I started, I say it's positive. Any other moment against it is negative. So reaction A will generate a moment at that point. So minus reaction A times the distance. The distance of at D from reaction A is 7. 4 plus 3. So 7 times 2.11. Another force before you get to reaction, you get to point D is 3. And that 3 is turning about point D. It's turning the same direction as the moment at D. So it becomes plus 3 times 3. That's the distance, equal to 0. That means MD is equal to 7 times 2.11 minus 3 times 3, that's minus 9. That's the moment at D. The moment at D is equal to 5.77 kilonewton meter. It's equal to 5.77 kilonewton meter. 5.7, that's the moment at D. Then moment at B. To get moment at B as a confirmation, because already we know what moment at B will be. Moment of B at D is supposed to be, moment at B is supposed to be 0. The reason is that the type of support at B does not resist bending moment. So it has a 0 moment. So we will do it as a confirmation to confirm that what we're doing is right, as a check. So I have moment at B. The same way, looking at A where we started, I say it's positive. Another one is negative. So B positive. Arrow A, which is against it, will be negative. And the distance from A to B is 4 plus this. This is 7 plus, that's 9. So you got of 9 times 2.11, which is reaction A. Then minus, because this is turning the same direction, arrow A is against, these ones are with it, so plus 3 times this distance, which is 5, plus 2 times distance 2, equal to 0. Because the reaction B, we have no moment at this location. So MB, moment at B, is equal to 9 times 2.11. minus 3 times 5 is 15. Minus 2 times, because they've gone over the sign of equality, so their signs are changing. 2 times, that is 4. This is equal to, if you work this, you will see that this is equal to 0 as a confirmation, the moment at D. So that is the bending moment in the structure. If you want to get the shear force in this structure, simple. Shear force is the algebraic summation of forces across the structure. Summation, you start from reaction A. Reaction A is 2.11. Is up, we say it's positive. It's going up, we say it's positive. So anyone going down is negative. So 2.11 minus, that's the shear force at A is 2.11. Shear force at A, 2.11 kilonewton. Shear force at C will be minus 3. 2.11 minus 3, which will give you, that's 1.89. Will give you 1.89 kilonewton. That is at point C. Shear force at A is equal to 2.11 kilonewton. Shear force at C is equal to 1.8. That's minus 1.89 kilonewton. Shear force at shear force at D is this, minus 2. That's minus 1.89 minus 2, which is equal to minus 3.89, because the shear force at C is negative. The one at D is also pointing down, so that's negative. So at B, the shear force at B so the shear force at B will close up at 0. That's this minus 2.89 plus the reaction will be equal to 0. So the bending moment diagram, let us get the bending moment diagram. Let's get the bending moment diagram. The bending moment diagram will look like this. The bending moment diagram is a graph of bending moment against distance. At A, the bending moment is 0. At C, the bending moment at C, the bending moment was the bending moment at C was 8.44. At C, the bending moment was 8.44, which was positive. That's let's say we mark it here. The bending moment, this 0 at C, 4. At D, the bending moment at D, that's MD, 5.77. That's something like this. At B, 0. So the bending moment diagram will go this way. Here, 8.44. Move to this point, 5.77, then to 0. So this place is 8.44. At this point is 5.77 kilonewton meter. Positive, that is the bending moment diagram. Then the shear force diagram. Shear force diagram be like this. At reaction A, the shear force was 2.11. 2.11. There's no other force until it gets to C. At C, 2.411 minus 3 gave us 1.89. That's the shear force. So as that's minus 1.89. It gets down to this at 1.89. This is positive. This negative. When it gets to D, at D the shear force rose. That the shear force got down further. Another minus to 2.89. Then at and closes at 3.89. That's the shear force diagram. So thank you for